Alright, yesterday we looked at pH. pH is the negative log in base 10 of the concentration of H plus ions. I also showed you the ICE method for dealing with weak acids. So this notation is molarity, basically. Moles of H plus per 1 liter. So on our scale of pH, we see 7 in the middle. We see 1 toward the acidic side. You can get smaller than 1. And 14 on the alkaline side. Let's spell that. And 7 is neutral. Water is exactly 7. Have you learned how to do logarithms? Do you know what log base 10 means? So log with some base b is equal to x. Log base b of y is equal to x. So if you have the expression y is equal to some base raised to the x power, and you plug in, so let's say I have 100 is equal to 10 to the x. What is the x? 10 to the x. What x gives you 100 when you raise 10 to what power? Well, what is 10 to the first power? 10. What is 10 squared? 100. So if I do log base 10 of 100, so here's my b, here's my y, I would get 2. A logarithm is a way of finding what this x is over here. The question, what power raised to the base would produce your y? So if the pH of water, so water pH, is equal to 7, how many H plus ions are in water? Well, I know pH is equal to the negative log base 10 of the concentration of H plus ions. You could undo a logarithm. So if I raise the base to the log base of y, I get y. Raising a base to the log b of that cancels it out. So if I raise 10 to the pH is equal to 10 to the negative log base 10 of the concentration of H plus. And let me make sure that's right. This negative is the same thing as 1 over 10 to the log base 10 of the concentration of H plus. And 10 to the log base 10, they cancel each other out. If you take 10 to the log of 10, it cancels each other out. So I get 10 to the pH is equal to 1 over the concentration of H plus ions. And if I do so 10 to the pH divided by 1 is just 10 to the pH. So cross multiply, I get the concentration of H plus is equal to 1 over 10 to the pH, which is equal to 10 to the negative pH. Negative just means to flip it around underneath. And the pH of water is 7. Long story short, water has a concentration of 10 to the negative 7 H plus ions. And this will be moles per 1 liter. Likewise, it has 10 to the negative 7 moles of OH ions per 1 liter. So a very small percentage of water molecules actually break apart, and I should really do this. The 2 arrow one. Break apart into H plus and OH ions. So a very small percentage of water molecules actually break apart into ions. So you can almost think of water as having both an acidic part and a basic part, or alkaline part. This is important for weak acids. So continuing where we left off yesterday, we found the pH of a strong acid. We found the pH of a weak acid. Now let's do a more complicated example. What is the pH of 0.1 molar sulfuric acid? And I'll tell you what the strong and weak acids are. This is a strong acid. But you have to be very careful with sulfuric acid. So, sulfuric acid is H2SO4. It is strong, so 100% of it will break into ions. But this is where you have to be careful. The ions that break apart into is H plus and HSO4 negative. So one hydrogen will break off first before the second hydrogen breaks off. The reason this is important is because HSO4 is a weak acid. So if we're starting out with 0.1 moles of this, again, we'll assume for brevity we have 1 milliliter. Then when this breaks apart, we'll end up with 0.1 mole of this and 0.1 mole of this. So it's a 1 to 1 to 1 ratio. When this breaks apart, then we have this weak acid that will not completely break apart. It will partially dissociate into H plus and SO4 2 negative. And to figure out pH, we need to know the final concentration of H plus ions. pH is equal to negative log base 10 of the concentration of H plus ions. We know how many initial ions we get just from sulfuric acid. But, and I believe that's pronounced bisulfate is one pronunciation of it. This is bisulfate or hydrogen sulfate. So this is where the ICE method comes into play. We have initial change in equilibrium. So initial, how much is changed, and what we'll end up with at equilibrium. So how many ions, how many bisulfate ions do we have? Well, we end up with this many to start. So we have 0.1 mole of bisulfate. How many do we currently have in the water? Well, we currently or initially have 0.1 mole. And we'll assume none of them have started breaking, that this has not started reacting yet, so we have 0 mole of sulfate. Well, some combination, some amount of these will break into H plus and sulfate ions. So this is going to lose some X amount. That means these will gain some X amount as it breaks apart. So at equilibrium, we have 0.1 minus X. We have 0.1 plus X here. And we have X right here. And we know that there's an acid dissociation constant. Ka. That is equal to the concentration of H plus ions times the concentration of sulfate ions divided by the concentration of the original solution, which is HSO4 negative. So our concentration of H plus is right here. That's 0.1 plus X. Our concentration of sulfate is right here. So that's times X. And our original final concentration of our starting one in the equation is 0.1 minus X. And let me look up bisulfate acid dissociation constant. It is 1.0 times 10 to the negative 2. I'll use an asterisk. One times 10 to the negative 2 is 0.01. So I'll just use it without scientific notation. Is 0.01 significantly less than 0.1? Would you say it is? This is something you get a feel for. I would say it's not. We'll do it both ways. So basically, would you say 1 is about the same as 1.01? I would say they are very close, but not. I wouldn't say they're equal. I would say there is a significant difference. I would say no. And this symbol right here, 2 equal signs, means significantly less than. One just means less than. One means significantly. I would not say the difference is significant. So solving this algebraically, I have Ka 0.01 is equal to 0.1 plus x times x. Someone at the door? So distributing x using algebra, 0.1 times x plus x squared. So x times 0.1 and x times x. Multiplying this to the other side, 0.01 times 0.1 minus x is equal to 0.1x plus x squared. Distributing this in, 0.01 times 0.1 is 0.001. And doing this times x gives you minus 0.01x. Moving everything to the same side. So I always like to begin it with x squared. So I get x squared. Moving this over here, I do it by adding. So it'd be 0.1 plus 0.01. So that would be plus 0.11x. And when I move this to the other side, I do it by subtraction. So that would be minus 0.001. So I have a quadratic formula. And I would plug it into the quadratic equation. So my a, so I have ax squared plus bx plus c is equal to 0. My a would be equal to 1. My b would be equal to 0.11. And my c would be equal to negative 0.001. And the equation for it is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. I get an answer of and again, only take the positive answer. So I get a response of 0.00844. Those two H's, isn't it? I round it to Actually, I'll just keep it in. So 0.00844288877. Good. Let's do the approximation real quick and see how accurate it would be. So we had 0.01 is equal to 0.1 plus x times x over 0.1 minus x. You're saying you said that 0.01 and 0.1, in your opinion, was significantly less than 0.1. So in that case, since these two numbers are since x must be so much smaller than 0.1, that means that 0.1 plus x is approximately equal to 0.1, and 0.1 minus x, I'd say this as a big F, is also approximately 0.1. That means we can replace this as our approximate and put 0.01 is approximately equal to 0.1 times x divided by 0.1. 0.1 divided by 0.1 cancel, and we get 0.01 is approximately equal to x. And the real value of it is the x is approximately equal to this, but calculating it, x is exactly 0.0084, and I'll round it to this many. So you're off by 15-20%. That's why I would have to solve this. I would not say that this is only off. This is a magnitude of 1. It's only off by 1 digit. We only need to add 1 0 in here to get to it. I would say 0.0001 versus 0.1, where we have 3 additional zeros, so this is 3 orders of magnitude, is when you could probably say that they're approximately equal. Or you would say 0.0001 is significantly less than 0.1 when you have 3 orders of magnitude. Well, that's only 1 order. But regardless, this x, what was this x? Let's go back to what we were doing. This x was how much additional H plus ions we gained. So our total amount of H plus ions, or total concentration of H plus ions, would be equal to 0.1 plus 0.008443, all equal to 0.108443. And to figure out pH, we simply do the negative log base 10 over concentration 0.108443. Which I get a pH of 0.9648. I guess pH really doesn't have units. I always like putting pH as a unit just because I don't really like naked numbers. But pH is technically unitless. You'd say something has a pH of 7 and 7 has no number or unit beside it. So this is very acidic. By the way, one of the, so this was for 0.1 molar sulfuric acid. I have some 18.3 molar. Let's go ahead and calculate, or I'll just go ahead and do it. So we want to calculate what that would be for 18.3. I think it's 18. I'll just do 18. It won't be much difference. So that means our change, we'd start out with 18. We'd add an x, and we get 18 plus x here. We'd start out with 18 moles of this and subtract x to get 18 minus x. And it doesn't matter for the other one. So, or Ka. So I get 18 plus x times x divided by 18 minus x. And our Ka was 0.01. Having my calculator solve that real quickly. That means our x is equal to 0.00998889. So our concentration of H plus would be 18.0.09989. That's been our 89. That's the negative log of that. Gives us a pH of negative 1.255476. So, if you can't already tell, this is very, 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 very strong concentration of acid. You do not want to accidentally drop a single drop on you, as it would be very, very bad. This is actually very dangerous to work with. And we sell it as drain cleaner. Which means if you go to the store and you get a bottle of drain cleaner, and you accidentally touch a few drops on your hand, or when you're pouring it into the water, it splashes up on you, you could significantly burn yourself. And it's free to buy, which means any person can go buy it, and if you have no clue what they're doing, they could significantly hurt themselves. Be careful if you ever buy drain cleaner. So 2 days ago, I started trying to do find the concentration of sulfuric acid, a percentage. I wanted to find volume per volume, but I couldn't. I wanted to introduce this formula here. I'm going to go ahead and do that now. So the concentration times the volume is constant. So the concentration times volume is going to be equal to the concentration times new volume. So let's think about this in terms where concentration is molarity. If I have a molarity of 1 mole per 1 liter, and let's suppose I have 1 liter. That means I have 1 mole in my glass. So I fill it up to the 1 liter mark, and I'm over here with 1 mole. Let's say I double my number of liters. So my volume is going to go up. That means my concentration must go down. So I've increased it to 2 liters. So I've doubled my volume. That means my concentration is now going to be 1 mole per 2 liters, or a half a mole per liter. So that would mean that I now have 2 liters, but still 1 mole inside of it. So when you take concentration times volume, it's basically tell you how much stuff you started with. It's still 1 mole. The molarity is 0.5 molar at 2 liters. The same gives you 1 mole of substance inside of it. Or 1 mole at 1 liter gives you 1 mole in that 1 liter. 0.5 mole at 2 liters gives you 1 mole in 2 liters. Does that make sense? If you change the volume, you would change the concentration, and it doesn't change. This equation here, it helps you figure out how to make a new concentration. So, for example, if I had 100% vinegar, and I wanted to make food grade vinegar, the stuff I could cook with, I wanted to convert it into 5% vinegar. As long as these concentrations are the same type, it doesn't matter what the concentration unit is. So let's say that I want 100 milliliters. I want 100 milliliters of 5% vinegar. My recipe calls for 100 milliliters of 5% vinegar for some reason, or I need to do that. So the original concentration times the original volume is going to be equal to the new concentration times the new volume. So this is the old concentration versus the new. So I want 5%, and I want 100 milliliters. I know the old concentration was 100%, but what's the equivalent volume that would have the same much vinegar in it, is the question. So you need to work without percentages. 100% is equal to 1. 5% is equal to 0.05. Thus, solving for V1 would be equal to 0.05 times 100 milliliters divided by 1, and that gives me 5 milliliters. So if I took 5 milliliters of 100% vinegar and I diluted it by adding 95 milliliters of water, to get it to 100 milliliters, the concentration would be 5%. Which makes sense, right? If you have 100 milliliters and 5 milliliters of it was 100% vinegar and 95 milliliters was water, then you would have 5%. If you put 100% vinegar, 5 milliliters, and then add it 95, then 5% of your solution would be, you'd have 5% vinegar. Does that make sense? So if you wanted to go from, let's say you wanted to do, you started out with 60% vinegar, and you wanted to make 30% vinegar, and you wanted 50 milliliters of it. The question is, how much water should you add? What should you do to get this? So that would be 0.6 times the original volume. That's what you're trying to solve for, and 0.3 times 50 milliliters. So your original volume of vinegar you should use, the concentrated vinegar you should use, 0.3 times 50 divided by 0.6, I believe is a half. So it should be 25 milliliters. So to go from 60% vinegar to 30% vinegar, basically you would do 25 milliliters of 60% vinegar plus 25 milliliters of water, and that will give you 50 milliliters of 30%. You're diluting it by half. So you take and you mix equal parts water to half the percentage. But this equation also works with molarity. So if I have 18 molar sulfuric acid, and I want 100 milliliters of 0.1 molar sulfuric acid, how can I make it? Well, I know on the left-hand side, so it's CV, my old numbers versus my new numbers. I know my concentration is 18 molar. I want 0.1 molar, and I want 100 milliliters of it. So my new, how much 18 molar sulfuric acid I would use would be 0.1 times 100 milliliters divided by 18 molar. It's equal to 0.55 carried milliliters, which is about half a drop. No, it'd probably be about 3 drops. About 3 drops of sulfuric acid to make yourself 100 milliliters of 0.1 molar sulfuric acid. So what I would do is I would, again, you never want to add water to acid. You always add acid slowly to water. So I would fill this up to about 80 milliliters. I would use a pipette to carefully measure out 0.55 carried milliliters of acid. And then after I mix them, I would slowly add water to fill it up to 100 milliliters. Again, you always add add acid to water slowly. Never add water to concentrated acid. So next week, we're going to be doing a lot of experiments. One of them I want to do is titration. I want us to, one, calculate how much NaOH is needed to make X molar solution of NaOH. And then I want to verify we made that amount. Then we will verify by using titration method. Titration, remember, is a method for figuring out molarity. Even if we didn't know how much this was, we could use titration to almost very accurately figure it out. And how I plan on doing it is with vinegar. I do have some 100% vinegar, which is very dangerous. And I don't know if I should dilute it first, but I'm kind of hesitant to dilute it as that introduces two errors. I know this is exactly 100%, and when doing titration, you want to know this one very accurately. I think it's alright to dilute it, because the problem is I don't have any distilled water, and it's a pain to make distilled water. You know how to make distilled water? What does it mean to distill? It's where you boil it and then collect it. So let's say I have some tap water with a whole bunch of junk inside of it. If I boil it, it'll turn into steam. And then if I somehow collect that steam by hooking up a pipe system to it, drip off into another one, what I end up with is very pure water. So how long does it take to boil water? And how difficult is it to collect all the steam without it going out to the side? So it takes a long time, and you don't make much. And unfortunately, we don't have a DI machine here. Another method is to make deionized water. It's a system of sponges and pores and rocks where you push water through, and these sponges and stuff trap all the ions so that pure water goes out the other way. Relatively pure water. We don't have a machine that does that. So the only way I know of getting pure water is to either buy it, which is very expensive, or to make it yourself. Because I'm willing to bet using tap water, we won't actually get the X we want. But we should be able to very closely verify how much we got. The tap water will neutralize some of the sodium hydroxide. And we do have a scale to measure it. So we should be able to get, and titration method that we're going to use is going to be very accurate. We might do it tomorrow also, because I'm not going to be here Monday. And did you finish your homework?